or the galactic center. And in fact, that is what I saw in the data.
So the gamma ray bursts were not coming from the area of the Milky Way. They were coming from all over the night sky. To Paczynski, this could only mean one thing.
Contrary to popular belief, gamma ray bursts could not possibly be in our galaxy, but instead they should be very, very far away, sort of at the edge of the universe.
Paczynski had thrown down a challenge. The neutron star theory, he declared, was wrong. The explosions had to be coming from something far bigger and far further away. The problem was that Paczynski's observations seemed to require explosions with more energy than any star had ever produced.
If you took a model that would work at the distances Baudin was describing, you would have to convert 1 million Earth masses into pure energy instantaneously, well, within 10 seconds anyway, and in the form of gamma rays, and get it out, and get it 3 billion light years to us. And so, yeah, okay, Baudin, maybe, but be good. Work on something else for a while.
When Bohdan Paczynski released his results, he was dismissed as mad. The only way Paczynski could be right was if Einstein was wrong, and E = mc squared was wrong. Paczynski must have made a mistake. He was soon forgotten, and so was his theory, until 5 years later, when he was to return with a vengeance. In 1991, NASA launched the BATSI satellite. Equipped with state-of-the-art detectors, it was going to study the bursts in detail for the first time. But as the data came in, a disturbing picture began to emerge. What they'd expected was that the bursts would line up with the galactic plane, meaning they were coming from within our own galaxy.
The first dozen or so gamma ray bursts weren't lining up with the galaxy. The next dozen or so also weren't lining up with the galaxy, but they happened to be randomly distributed throughout the sky.
Once again, the first thoughts of the scientists were that someone must have made a mistake.
I think the immediate reaction was perhaps a little bit of disbelief, that they must be doing something wrong. And of course, ourselves, we were worried about that and worried about it every night when we tried to sleep.
And yet, as every day went by, more and more bursts appeared all over the sky.
We said, well, this is going to cause a lot of waves, but we better go public with this announcement that it looks like the gamma ray bursts are uniformly distributed throughout the sky.
There was now no doubt. Paczynski had been right all along.
I think that was professionally the most joyous moment in my life, because all of a sudden I realized that something which was very risky, which could work either way, turned out my way. So, of course, I was very, very happy.
But Paczynski's triumph threatened to plunge science into chaos. If the bursts were coming from beyond our galaxy, then they had to be caused by something far bigger than science could explain.
If they were really coming from distant galaxies, it was a phenomenon unlike anything we've seen before. The amount of energy release, the rate of energy release, was greater than anyone had ever seen before in any other form. and the details of how you got that, nobody could understand how that could be. It was pressing the limits of our understanding.
It was now clear that these explosions were of an almost inconceivable size. So big, in fact, that they might even be violating Einstein's fundamental law, E equals mc squared. And that was meant to be impossible. It now became imperative to get an accurate distance measurement of the gamma-ray bursts. Scientists turned to the only technique they had for precisely measuring how far away objects are from Earth. A technique called redshift.
Redshift is a fantastically important tool for astronomy. Basically, measuring the redshift to an object is what tells us the distance of that object in astronomy. And the distances that we're talking about are so vast that they're extremely hard to measure by any other way, but redshift actually turns out to be quite straightforward.
Most explosions cause a flash of visible light. Scientists can split this light into its spectrum of colors. The further away an object is from Earth, the more red the light looks. The problem with gamma-ray bursts is that they produce no visible light, so they cannot be redshifted.
Even today, we cannot focus gamma rays. There are no lenses that will make an image in gamma rays.
But then they realized that when the gamma rays blasted out, they would pass through all the gas and dust floating in space. This material would be heated up and would glow. This afterglow would be visible and might last for several days. If they could find it, it could be redshifted.
If we could ever find just one glowing ember of a gamma ray burst, the mystery would be cracked open, because we'd have a location and we could go look with the full panoply of radio telescopes and telescopes in space and big telescopes on the ground.
The hunt was now on for the afterglow. On the 9th of May 1997, a very bright gamma-ray burst was picked up. All over the world, telescopes were being reprogrammed and refocused in the hope of catching this elusive afterglow. And then it happened. A faint flash of light was spotted. The astronomers analyzed the light. It wasn't at the blue end of the spectrum, suggesting the burst was from inside our galaxy. The light wasn't even green. The yellow would have indicated that the bursts were coming from far outside our galaxy.